Okay. Well, luckily, both professors seem to be covering very similar topics. So Dr. K and Dr. M are both looking at limits on the most recent homeworks. Also, rectangular and spherical coordinates. You don't have a mic. Okay, well, I will change that. Okay, you should have mic access now. Okay, so I thought about just starting with limits. And here we're just looking at functions of two variables to learn some lessons about limits and multivariable calculus. Okay. So I have a sense that there are 3 people from Dr. M's class and a person from Dr. K's class. Okay. So here we're taking limits of functions of two variables. So these are functions of some subset of R2 into R. Okay. In particular, we're going to be looking at limits as points in the plane in the domain of our function approach the origin. Okay. And the big idea is that just like with one variable calculus, for a limit to exist, the limit from the left and the right agree. So the limit as in one variable calculus as x approaches some number from the left of a function has to exist, and the limit as x approaches a from the other side, the positive side, has to exist, and they have to agree. And then we could say that the limit in general exists. But of course, we're in 2 dimensions for functions on R2. So there's more than 2 directions, right? There's not just a left and a left from the left and from the right. There's from any direction towards the origin. And even worse than that, there's really any curve that goes to the origin. So for a multivariable, for a function of 2 variables, for the limit to exist, as we approach the origin, this limit has to be the same for all possible paths going to the origin. And not just straight lines, but all possible paths. So, in a sense, as soon as you find 2 different paths towards the origin for which the limits are different, you can, it's easy to show that the limit doesn't exist, right? We're not talking about continuity yet. That's a good question. This is very much related to continuity. We're just talking about a limit existing. Yeah, so recall that for when we think about limits as points approach a specific point, we only care about the behavior of the function around the point. With limits, we don't care about what actually happens at the point quite yet. It's with when we talk about continuity, then we start caring about not only how the function behaves around the point, so limit, but also what the function does at the point. So right now it's just limits. So how the function behaves around a point, not what it does at the point. Okay. So let's look at some examples that should be beneficial to both classes. Okay. So let's look at the limit as points in the plane approach the origin of this function. Okay, so what I would do is I just first do a quick spot check, right? If the limit does exist, it has to be the same regardless of whether you approach the origin along the x-axis. So we're going to try the x-axis. So approaching the origin along the x-axis. And it should be the same as if we were to approach the origin along the y-axis. Okay. So we're going to try the y-axis as well. And if we get two different numbers, then we can stop and say, well, the limit doesn't exist because we got two different numbers, right? The behavior of the function depends on the approach to the origin. So let's try the x-axis. So what does that mean? Well, what equation defines the x-axis in the plane? That's right. Every point on the x-axis, recall, has a y-coordinate, which is 0. So y equals 0 is exactly the equation of that horizontal line, namely the x-axis. So we can look at the limit as points along the x-axis, so y is 0, okay, which of course gives us license to replace y with 0. Okay. Sorry, I forgot. So we get, if y is 0, we get minus x squared over x squared, which reduces to a constant. Remember, x is not 0 because we're approaching 0, we're not at 0. And we all know the limit of a constant is that constant. So along the x-axis, the limit is -1. We will now try the y-axis. And this is kind of like what my initial kind of check is, just to, because this is the easiest thing to check for. So along the y-axis, we know that every point on the y-axis has the x-coordinate of 0. So we take the limit as 0y goes to the origin. And this gives, we can now replace x with 0. And then we see that we get a constant, namely 0 over y squared, so 0. Okay, so we see that the limit, if we approach the origin along the x-axis, is -1. On the other hand, along the y-axis, it's 0, so we can conclude that the limit does not exist. Okay, so, all right. So let me just, so for the next example, we'll see that maybe we can approach the origin along some arbitrary line, which is not necessarily vertical nor horizontal, right? So maybe we can check a line that has a certain slope. Okay. All right, so we can check either along the line where y equals mx, and of course we're approaching the origin, so we don't have a, well, so this is any line through the origin. Or equivalently, we could replace x with some slope times y. It doesn't matter which way you look at it. So the second example, we will take a limit of the following function as the arguments of the function go to the origin. Okay, and if I reproduce what I did previously and just go along the x-axis, you can quickly see that if y is 0, we get a limit of 1. Because we get x plus 0 squared divided by x squared plus y squared, or 0 squared. So that expression simplifies to 1. So the limit will be that constant 1. And likewise, along the y-axis, defined by the equation x equals 0, we get the expression y squared over y squared, which reduces to 1. So again, we were taking the limit of a constant, so we just get the constant. It looks like the limit is the same along as we approach the origin along the x and the y-axis, but maybe it'll be different if we approach the origin along some slanted line. So we're going to check. So this is a non-vertical line. Okay. And so I'm going to say, well, let's take the limit as x, and then we're going to replace y with mx. So this way we're approaching the origin along some line. Of the function. Okay, so we get to replace y with mx. So we get x plus mx squared on top, and we get x squared plus y squared on bottom. Okay. So now we reduce this expression so we can get some nice cancellations and try to evaluate the limit. So it looks like here we get on top, we can factor out a x squared, and we're left with 1 plus m squared. On bottom, we can also factor out an x squared. Right, so we have that cancellation. And now notice we're taking a limit of an expression that does not involve x. Right, so as far as the limit is concerned, as x goes to 0, m doesn't care. It's its own little thing. So it's like a constant as far as taking the limit is concerned. So we get a limit which depends on the slope. And the lesson there is that choosing different m's, different slopes for our line, results in different limits. Okay, so here the limit depends on m, right? So the limit could be different. So if we chose the line y equals x, m would be 1, and in that case our limit would be 2 over 5. But if we instead chose the line y equals 2x, the limit would be, well, m would be 2, so the limit would be 3 over, over 2. Limit would be 1. 3 over 5. So to get different limits. So the limit doesn't exist. Yeah, because they're doable problems, we could approach some other points that are not the origin, but it's just a matter of translation. So if you're approaching, if y are approaching, say 3 and 4, you could always just shift the origin to the point 3 and 4, and so if you let u equal x minus 3 and v equal y minus 4, then you see that as x and y approach the point 3 and 4, we see that the point uv approaches 0, 0. So we can always restate these limit questions in terms of approaching the origin. And it's really just for ease for the student. Yeah, because all it took is to taking the xy plane and translating it to a new origin in the uv plane. Okay. All right. So the next example is going to be one where I believe it turns out that the limit would be the same if we approach the origin along any line. So you can take any line you want, vertical, horizontal, slanted, and you can approach the origin, and it turns out the limit would always be the same. But if you take instead a curvy path, as it turns out, interestingly enough, you would get a different limit. So let's look at an example like that. So the lesson there being that it's not sufficient just to look at all possible lines going to the origin. We also have to look at curves. So which one is a good one? This one's good. Okay. So if you do a quick check, if x is 0, so you're approaching the origin along the y-axis, you would get the limit of 0. If y is 0, so you're approaching the origin along the x-axis, the limit is also 0. You would maybe then try arbitrary lines through the origin, and you would get, let's see what this expression would reduce to. You would get, again, if we're going to the origin, x must go to 0, so this would go to 0 as x goes to 0. Because we're approaching the origin, of course, both x and y have to go to 0. So just quickly, just checking approaches along the line would not be sufficient. We would always get the limit of 0. But we would need to know that we don't stop there, right? We have to check curves. So we're going to check approaches to the origin along some curves of the form y equals x to the power n, or x equals to, or you can also try, it doesn't matter. Okay. So notice what that is. It's just like a polynomial that goes through the origin. So we're going to be approaching the origin along this polynomial curve. Okay. So, I mean, you might not know what like this might be. Here I'll tell you really quick. See, suppose n is equal to 3, and I chose 3 because I have a y squared. So if I were to replace y with x cubed, y squared would become y to the power 6. Sorry, x to the power 6, which would match this. So that would be my first guess. So let's take a limit as x, and then y, which is x cubed, goes to the origin. All right, so our expression then reduces to x to the power 6 in the numerator, because I replaced y with x cubed, and then 2 times x to the power 6. Okay. And of course, this reduces to the constant of 1/2. So the limit would be 1/2 along that curve. But we already noticed that if we approach the origin along, let's say, one of the axes, the limit would be 0, right? So the limit would be 0. So we found 2 different approaches with 2 different limits, so the limit in general does not exist. Okay. So the next thing we'd want to try, so it's possible that maybe the limit exists along all lines and like kind of polynomial curves towards the origin. So maybe we can try polar coordinates instead. Okay. So the last thing we can want to look out for is trying polar coordinates. Okay. So this is, recall that you know x would be r times cosine theta, y is r sine theta, and in particular, notice that since r is the distance from a point, between a point xy and the origin, we notice that as we approach the origin if and only if r itself is approaching the origin 0, and of course from the right, because r is positive, it's a distance. All right. Let's see, so maybe I have a well-known example here. So I know that I try to use polar coordinates if I see a lot of x squared plus y squared business going on. Okay. All right. So this is our next example where I'll try using polar coordinates. And if we try to evaluate directly, we don't have a denominator, but we would get that the first factor goes to 0, and the second factor here goes to -infinity, because remember log. Yeah, as the argument of log approaches 0 from the right, log approaches -infinity. And this is, as you recall, indeterminate. 0 times the square root of infinity is indeterminate. Okay. So I'll try to prove that the limit exists by using polar coordinates. So we know that we approach the origin if and only if r approaches the origin from the right. And in polar coordinates, the square root of x squared plus y squared is r, and x squared plus y squared would be r squared. So, of course, if you get an indeterminate form here, So if you get 0 times some sort of infinity, there is a standard trick that you use. Namely, you want to get this into the form, an indeterminate form, which is L'Hopital friendly. Say infinity divided by infinity, or 0 divided by 0. Okay, these are indeterminate but L'Hopital friendly, if you will. So the trick is to rewrite this factor r as the reciprocal of its reciprocal. Right? 1 over r is just r. So if we try to evaluate the limit, we get negative infinity in the numerator, and now positive infinity in the denominator, right? In terms of limits, 1 over something that goes to 0 from the positive side is positive infinity in terms of limits. All right, so it's still indeterminate, but it's L'Hopital friendly. So we go ahead and apply L'Hopitals here. Well, I should have used properties of logs first, right? So maybe make a note that I'll write log of r squared as 2 times log of r, and r is positive, so it's defined. And then we would differentiate. So on top, we get the derivative of 2 times log of r, so 2 times 1 over r. And the denominator we differentiate with respect to r, and we get this, which we in turn simplify, and now we can evaluate the limit directly as it turns out. We get 0. Okay, so the limit would be 0. So the limit here does exist, using polar coordinates to essentially turn this problem in 2 variables into a problem in 1 variable, using the fact that we approach the origin if and only if the distance to the origin r goes to 0 as well. Okay, let me check. I should be checking chat. 1 second. I have it on the wrong panel. Okay. All right. So yeah, so what if you keep checking along various paths to the origin and it seems like the limit seems to be the same regardless of the path? Then maybe you're getting an inkling that the limit does exist. So the question is, how would you then confirm, prove, convince your grader that the limit exists? So let's see, let's look at a problem the limit exists, and then you might have to use inequalities because of the definition of limit. So, okay. So here are some basic facts that you might want to use about when trying to prove that a limit does exist. Right, so you might possibly could use the fact that, let's say, we know that okay, let's do it this way. So you know that x squared is going to be greater than 0 if we're taking a limit. Oh, sorry, greater than or equal to 0. And if I add y squared to both sides, the inequality still holds. And now, because we're taking a limit as we approach the origin, this is not 0 yet. We're not at the origin, we're near the origin. So we can divide by it. So hopefully this is clear that this expression where you have like x squared over both x squared plus y squared is less than or equal to 1. Okay. In fact, if you have some even power of x or y in the denominator, that'd still be the case, right? Because the same argument holds. So, like, this is especially, I guess, I'm mentioning this because of Dr. K's homework. So clearly, y to an even power, like 6, is non-negative if you add x squared or any positive quantity, any quantity to both sides. You'd still, after you divide, you would get that this expression is less than 1. All right. That's one of the inequalities I wanted to mention. I think there was another one, and I forget what it is. It'll come back to me in a second. So, and you also want to know the definition of limit, right? So, the limit exists let me just say equals L. Yeah, that's what I meant to say. So the limit exists if for any point in the domain, if x and y get close to the point they're approaching, namely 0, then when you evaluate the function at that point, the output of the function gets arbitrarily close to the limit, the epsilon close. Okay. So in particular, notice what this means. If you rewrite this in terms of distance formula, this is telling us that the distance between the between point x, y, and the origin, which is square root of x squared plus y squared, is less than delta, will then imply that the value of the function is arbitrarily close to the limit. So here's a limit that actually does exist, and we're going to try to prove that it does. Okay. So this limit turns out to be 0. You can try all sorts of approaches to the origin, you'll get 0. So we're going to try to prove that if we're at a point delta close to the origin, then we're going to show that the value of the function, the absolute value of the difference between the value of the function at the point and the limit, which is 0, is arbitrarily small. Okay. Of course, that 0 goes away. And notice, look for things like this, right? Notice we have x squared on top as a factor, and then we have this denominator. Okay, so I'm going to split this up. And I'm dropping the absolute value bars because everything is positive when we have even powers. Okay, and then we have absolute value of y, where I'm going to leave the absolute value on the y because y could be negative, right? But we need absolute value. Okay, and so can somebody tell me what do we know about this quantity? What do we know about this expression from what we just talked about? No, I'll probably repeat the argument. we know that y to an even power is not negative. Adding x squared to both sides doesn't change the relation between the two sides. Right. Dividing by this zero quantity because we're not at the origin yet. Okay. We get that that expression is less than 1. Right. So we get that we can replace this with a factor of 1 and then leave the absolute value of y, but that whole result is less than or equal, or greater than or equal to what came previously. Okay. Oh, I think this is what I wanted to mention. And, well, you can stop right there because what happens as we approach the origin, right? Y has to eventually approach 0, right? If we're going to the origin. So y has to go to 0. So right away you see that this would go to 0 as we go to the origin. So in a sense, it's a squeeze theorem. We have that at the limit, well, we get this inequality. Let me be more formal about it. We've proven that the absolute value of our function is less than or equal to the absolute value of just y. And if you think of squeeze theorem, we would then take a limit as we approach the origin. And we see that the limit on the right-hand side is obvious. As we approach the origin, y has to go to 0, so the right-hand side becomes 0. And you've essentially used the squeeze theorem to prove this limit is 0. Okay. Okay, all sorts of little mistakes here. All right. Because what this is telling us is that the limit of our function is somewhere between 0 and 0, right? So it must be 0. Okay, so the limit exists, and we're done. You could have also used like an epsilon delta thing, which I was going for initially. I was going to have that our function evaluated at point xy minus the limit is less than or equal to the absolute value of y. And because we know y squared is smaller than x squared plus y squared, and you take the square root of both sides. The square root of y squared, we should all know that is absolute value of y. And this is exactly, we would want to make this is less than delta by assumption. So we're assuming we're sufficiently close to the origin. And we can simply let delta equal epsilon, and you would get your inequality, your epsilon delta proof. So it would be sufficient to define epsilon to be equal to delta in this problem. Okay, but I just realized maybe squeeze theorem seems a little bit easier to think about than epsilon delta. All right, what else can I say here? Before we move on. Oh yeah, so just two more limits, and then so this is really for Dr. K's class. It's a little trickier. So here we see that we don't have x squared plus y squared. We have x to the power 4 plus y to the power 4. Okay, and it would be nice if you could use this idea that approaching the origin means the same thing as letting r go to 0. Okay. But it's so we can't use the fact that r squared is equal to x squared plus y squared over here. But there are some, again, playing around with inequalities. You can essentially squeeze this limit to be 0. Okay. So what can I do? So notice that x squared plus y squared would give you a bunch of terms if you either use binomial expansion or just FOIL it out. Okay, and what do we know about? Well, we know that this is positive or non-negative. Well, it is positive in our case. It's positive. And so if you drop the middle positive term, so drop this positive term, the resulting expression you would get would have to be smaller, right? Because you took away some positive quantity from the left-hand side of that inequality. Okay. So what we can do is we can start playing around with the inequalities. And realize that this factor is smaller than x squared plus y squared quantity squared. So the whole product here becomes bigger on the right-hand side. Is that okay? All right. But now we see that we can do our substitution where r squared replaces x squared plus y squared. So we get r to the 4th over here times log squared of r squared. And if we want to take a limit as we approach the origin, that's equivalent to taking a limit as r approaches 0 from the positive side. And then using L'Hopital, so sorry about that. So here you would get 0 times infinity. If you try to evaluate directly, it's indeterminate. So we attempt to re-express this in a way so that we get a L'Hopital friendly indeterminate form. And we get infinity over infinity, which is now L'Hopital friendly, and you apply L'Hopital's rule, and you would get 0. So, well, let me take the 2 out first, sorry, 4, and then 2 times log r, 1 over r. Okay. So we can simplify this but again, we would get an indeterminate form. But if you apply L'Hopital's just one more time, so use L'Hopital, and you would get 0. So the limit is 0. So now we get a determinate limit to 0. Okay. I know Dr. M in the limit problems, there was he wanted to warn you about something when you're using polar coordinates, so I'll show you what that is. Let me just clear everything out. So when trying to prove a limit using polar coordinates, there's a danger. So what has to be true? So the limit will exist if r goes to, if the limit is independent of theta. Okay. So the limit has to be independent of theta, but there's a danger that you can get a function of theta which is unbounded. So I'll show you what I mean. What is it? Okay, this is good enough. Okay, so first of all, I guess notice for the function that it's not defined at the origin because we're dividing by 0, but it's also undefined along the whole curve where the denominator is 0. So that's some sort of circle. If you complete the square, you'll probably, what is it? Completing the square, you get a circle of radius 1/2. Okay, but anyway, so here if I try to use polar coordinates, of course we replace x with r cosine and y with r sine. So we get r cubed sine theta cosine squared theta and r cubed sine cubed on top. The denominator, this becomes r squared minus x, which is r cosine. And then we can simplify this. How can we simplify this? So we can factor out r in the denominator and the numerator. I can see that I can also factor out a sine from the numerator. Oh, and I would be left with a r squared here. Okay. So we get some nice cancellations. This becomes 1, Pythagorean trig identity. Okay, so we get, I'm going to write this as r squared and then times sine of theta, r minus cosine of theta. Okay, so now the mistake that some people would make is that, okay, r is going to 0, so this factor is going to 0, right? And this r is going to 0 as well, so you have 0 times some function of theta at the limit, but it doesn't matter what theta is, right? Because 0 times something is 0. But the problem is that this is not bounded. This could blow up to infinity by choosing, if you think of theta as your angle of approach towards the origin, depending on our angle of approach to the origin, maybe this expression is not finite, maybe blows up. Okay, so that's not bounded, so this is a mistake. The limit is not 0, it doesn't exist in fact. So if you're going to use polar coordinates, sure, you want, r to go to 0, but this function of theta that you get here has to be bounded for the proof of the limit existing being valid. If it's not bounded, you have to do something else. In fact, what if we go back to rectangular coordinates and try to approach the origin along the line where x equals y squared? So let's do that. And this is going to be the last limit that I think we can do today. Crap. So I'm going to approach the origin along this parabolic curve where x equals y squared. Okay. I'll write down the original function for clarity. And so we get to replace x with y squared. I always forget to write the limit statement correctly. So we get y to the power 6, 5, sorry. And so notice here that if we replace x with y squared, we do have a nice cancellation. And now we can reduce this to something went wrong. Oh, I forgot to replace this x with a y, so that would become y to the power 4. My bad. So we get
is it y to the 5th? Like on the numerator?
in the numerator, it's y to the power 5. Yeah. Is that wrong?
Wait, aren't you doing y squared?
X equals y squared.
Oh, x equals y squared. Okay.
Yeah. So yeah, that would be. So yeah, y to the power 5 in the numerator. But of course, here, if you evaluate the limit, you're going to get plus or minus infinity, depending on whether y is negative or positive. Right? You get y plus 1 over y. So the first term goes to 0, but the second term goes to plus or minus infinity. So this is, the limit doesn't exist, right? Okay. So that's just a warning that Dr. N had on his homework about polar coordinates. This function of theta here has to be bounded. All right. So you can ask me any questions now before we move on to like cylindrical and rectangular coordinates. Give you a breather or something. Let me get a drink of water here. No, because I've never, this is the first semester they're teaching this course, so I don't have any experience. We can maybe gather, but it's also two different professors, not coordinated sections, so I don't know. If anybody wants a review, I guess I'm free. When is your exam? And in which class? For Dr. M, the 26th, and 23rd. Okay. Yeah. I mean, we can probably meet. I'm probably available like on a Sunday at best. Otherwise, I'm working every other day. So we can probably cook something up on a Sunday if you like. All right. I'll put something together then. All right. But it wouldn't be like I know what's on the test because I really have no idea. I've never seen any of these tests for this course. So it's more going to be like bring questions and we can go over them. Yeah. All right. So the next thing is rectangular and spherical coordinates. So you're probably more familiar with rectangular coordinates because it's just an extension of polar coordinates to 3 dimensions. So we know that in the xy plane, we can denote the position of a point with coordinates, of course, but we can also specify that position by saying how far away the point is away from the origin, and giving a kind of like a direction or slant for the where the point is by specifying the angle as measured from the positive x-axis counterclockwise. Right? So, and if you we know that tangent of that angle will be y over x because this is like the y. Y is the opposite side of a right triangle, x is the adjacent side. And okay, so this allows you to relate x and y to r and theta, if you will, right? But you might want to go the other direction. So maybe you want to define x and y in terms of r and theta. So we all know that x is cosine theta, r times cosine theta, y is r sine theta. Okay. And here we're going to limit r to be, say, well, doesn't matter, but we're going to say r is positive and non-negative as it's a distance. Then if you add a third dimension, so you have the two-dimensional xy plane, and then the third dimension is z, where z is just going to be equal to itself, if you will, right? All right. So an important thing that you'll be doing is expressing regions in the xy plane in terms of regions in the r theta plane, or theta r plane, so to speak. So you might say, well, okay, suppose that theta goes from 0 to pi over 2. And let's say r goes from 1 to 2, right? So in the theta r plane, that's a rectangle. Okay. And so you'd want to be able to see what the corresponding region is in the xy plane. Well, we know that in the xy plane, r is a distance. So if we kind of, as a guiding thing, draw a circle of radius 1 and a circle of radius 2, right? So this region is all points where r is between 1 and 2. So that would be this angular region, right? All points which are at least a distance 1 away from the origin, but at most 2, is this angular region. Right, so that's comes from R being between 1 and 2. Yes, yes. So I'm sorry, you're anticipating what I was going to do next, and that's I'm going to then say, well, what about the region where theta is between 0 and pi over 2? Well, on the xy plane, theta is the angle we make with the positive x-axis. So theta equals 0 corresponds to points on the positive x-axis. Theta equals pi over 2, 90 degrees, corresponds to points on the positive y-axis. So the first quadrant is described by this green inequality, right? Oops, I didn't mean to do that. But so putting those two together, we see that the region that satisfies both is just a quarter of that angular region in the first quadrant, right? So the corresponding region in the xy plane is corresponding to this rectangle, and the theta r plane is that quarter of a washer, right? I'm using the math term angular region, but yes, it's a washer. So you have to be able to play that game, right? Be looking at the bounds for theta and r, seeing what the corresponding picture is in the xy plane, and vice versa. So not that I'm aware of. It's just a standard question that I don't know if it's on your homework or not. Okay. So what about this region in the xy plane, where the region is a triangle with some vertices here. Okay. So here we can say that maybe x is between 0 and 1, but y starts on the line where y equals 0, right? So that's the x-axis. But then y increases and it hits the line where y equals x. So we can say that y is between 0 and the line where y equals x. So it's a triangular region. So can we describe this region in the corresponding region in the theta r plane? So theta is easier to do here, because we imagine that theta is like, you know, if you're on the x-axis, what is theta? 0. But as theta increases, you eventually approach the line, this diagonal line where theta equals pi over 4. That's right. Each point on this line, because the slope is 1, so tangent of theta would be 1. So that's defined by where theta is pi over 4 in the first quadrant. So theta is pretty easy. Theta is between, well, I shouldn't say easy. It's never easy. 0 to pi over 4. Okay. So what about r? Well, yes, r is the distance to the origin, right? It's a hypotenuse of the right triangle. But if I'm covering this region, this two-dimensional region, notice that if you try to cover this region in a polar fashion, you start at the origin and you go out, right? And then you increase theta and you start at the origin and you go out. So I'm covering this region in this radial fashion, in this polar fashion. So r actually varies. At the origin, r is 0. Okay, and as we move along the line, we reach some maximum value of r. We let r increase until it hits the line where x equals 1. But it's not 0 to 1. And at the risk of making this really busy, if I let r go from 0 to 1, I would be covering a sector of a circle. Oh man, undo. The upper bound for r is actually not a constant. You're not covering just a slice of pizza here, you're covering a triangle. So the extent, the distance you go away from the origin depends on theta. I'm going to redraw this triangle now. How much time do we have? Oh crap, okay. All right. So this is theta. Notice that we would let theta go from 0 up to the line where x equals 1. So think of a right triangle where the adjacent side relative to theta has a length of 1. Okay, and the hypotenuse, as somebody said, is r. It's the maximum value of r. And this is the opposite side. So we can use trigonometry, right? We can relate the adjacent side to the maximum value of r by using cosine. So cosine of theta is adjacent side divided by the hypotenuse. So r would be 1 over cosine theta. Okay. So r would start at 0. The opposite is not 1. The opposite side increases as we move up the triangle, but the adjacent side is always 1. Okay. So yeah, well, this point is not necessarily at 1, 1. It's at the point 1, y over here somewhere. Okay. So the opposite side changes heights, if you will. It's the adjacent side which always remains 1 in this triangle. Okay. So r starts at 0, but then it increases till it hits its maximum value when we hit the line where x equals 1. And so at that point, r equals 1 over cosine theta. Right, so you would have to graph that. So at 0, we get 1. As theta approaches pi over 4, we decrease. I don't know, it's some funky curve. So this region is something like that. So that's a little bit more difficult. All right, we're almost out of time, so I guess spherical coordinates will be for next time. But I want to mention something from Dr. K's class, because the problems he gave you weren't easy, I don't think. They're interesting, very interesting. So he offers you a problem where we have a function of r and theta. So this is still in rectangular coordinates. And it's something like r squared minus 2 plus, let's say, cosine of 3 theta, right? And you're supposed to rewrite this equation in rectangular, or we write this function as a function of xy, and so we write this expression in rectangular coordinates. Okay. So there's two things. So to use rectangular coordinates, we want to take advantage of the fact that x squared plus y squared is r squared, and the fact that x is r cosine and y is r sine. But it's hard to use these two if your trig function isn't just like cosine of theta by itself or sine of theta, but it's like cosine of a multiple of theta. So you have to use trig identities. Well, I shouldn't say have to, maybe there's other ways to do it. You want to use trig identities to write this as functions in terms of just sine theta, cosine theta. Okay. So what I can suggest to express processes, like the formula for cosine of 2 theta. You can rewrite this in terms of just cosine theta and sine theta by using this identity. And similarly, you probably are familiar with the identity for sine of 2 theta. It is 2 times sine theta cosine theta, right? All right. And if I wanted to, so that's the first step, rewriting everything in terms of just cosine sine theta. And now I see that cosine theta is x over r, and sine theta is y over r. So the next step would just to be replace cosine squared with x squared over r squared. And sine squared will become y squared over r squared. And then once you just have x's, y's, and r's are easy to replace. Because r squared we know is x squared plus y squared. Okay. So similarly over here you could have 2 times sine becomes 2 times y over r times cosine, that's x over r. And then r squared is especially easy to replace with rectangular coordinates. Okay. So it's actually replacing cosine and sine theta and r squared in rectangular coordinates is the easy part for the problems. The hard part is using these trig identities. Okay. So I was going to show you a little trick. So what if there were a formula which allowed you to get both trig identities at the same time? And to do that, we might have to go through the complex plane. So you would want to know Euler's identity, or one of the identities, right? So it says that cosine of theta plus I, so that's an imaginary number, sine theta, is the same as e to the I theta. And why am I dropping all the letters from the words I spell, huh? All right. So for example, if I wanted to derive the identity, the trig identities here for cosine 2 theta and sine 2 theta, I'll just put them into this complex expression and then use Euler's identity to say that this is the same as e to the I 2 theta. And then trust that properties of exponents hold for complex numbers, so I can then write this as e to the I theta squared because of properties of exponents. And then you can use, for the e to the I theta, you can use Euler's identity again. Okay. I'm going to need some space for this little. So now I'm just going to expand either using binomial expansion, if you have very high powers, right, where you can't just FOIL easily, or just FOIL. So we get, let's see, what do we get? We get cosine squared plus 2I cosine theta sine theta plus I squared sine squared, if we FOIL that out or use binomial expansion. So next, what you want to do is gather the imaginary parts of the real parts. And by the way, what's I squared? Yeah, -1. So this becomes -1, and so I can lump it in with the real part. And then we have plus I, and this is the imaginary part. It's getting multiplied by I. And so the idea is that for two complex numbers to be equal, oh man. For two complex numbers to be equal, the real parts, so the parts that don't get multiplied by I, have to match. And of course, the imaginary parts, the ones that get multiplied by I, have to be equal as well. So this is a, clever identity in the real numbers that can be more easily derived if you go through the complex numbers. So we recovered the two trig identities for sine 2 theta and cosine 2 theta. And there would be nothing stopping you from doing this for, like, say, identities for cosine 3 theta and sine 3 theta. Exactly the same process. Going to wrap this up into a complex number, use Euler's identity, use properties of exponentials here, rewrite what's inside the parentheses using Euler's identity again, apply binomial expansion, so I'll just do that quickly. The cosine cubed plus I cosine, or 3I cosine squared plus 3, and then cosine theta I squared sine squared, and finally I cubed times sine cubed. So you might want to review binomial expansion. It's related to the thing called Pascal's triangle. That's where you take a plus b to some power n and you expand it in a formulaic way. Okay. So now let's gather all the real parts. So let's see where they are. This is the real part. I squared is -1, so this will become the I will go away. And these are, so let's see, I squared will become -1. I is I cubed will become I squared times I, so that's -I. So I gather the real parts. Then plus I, and I'm going to gather the two imaginary parts. Remember, that's minus I, factor out of I, so I'm left with a minus. Okay. And so that should be equal to what we originally had. And then we know that we can equate the real parts to each other. So cosine of 3 theta, we derived an identity where we can rewrite it in terms of just cosine theta and sine theta. And then the imaginary parts. So we've derived a trig identity for rewriting sine of 3 theta in terms of just sine and cosine theta. And once you would do that, then you can go ahead and replace cosine with x over r, and sine with y over r, where r we know is. Anyway, I think that's all we have time for. So I guess I'll need to do spherical next time. Well, thank you, and we'll see you in the tutoring lab.